All right, so here is a three-way lamp. I don't know if they still sell them. Okay, so you plug this to the wall. When you close this switch, just the 100-watt bulb glows. And then you turn it again, and you close both the switches, and both the 100 and the 75-watt bulb glows. So now you have a 175-watt bulb. And then you close again, and then just the 75-watt bulb glows. So this bulb has three settings: 75 watts, 100 watts, and 175 watts. And you can do any combination: 50, 100, 100, and so on. So in a dipping light, you can change the resistance continuously and change the current. Yeah. So here's what three-way prong plugs do. Current will find the least path of least resistance. Yeah. So let's say you have a two-prong plug device, so current flows through there, and let's say this malfunctions, and then this wire is hitting the housing. In this case, the current will go through the housing and then through you to the ground. And that could be bad for your health. So how do you solve that problem? So now in three-way prong devices, now there's a wire connecting to the housing of the device. So if something malfunctions, the current will go through there, which is grounded. That path has less resistance, so the current will go through there rather than through you. Yep, so that's that. You saw household wiring. Houses, in a house, all those plugs, every plug is connected in parallel. So if this is malfunctioning, all those will work. Okay. So if your washing machine goes bad, your TV will still work, and so on. So all the wiring is connected in parallel. All the houses themselves are connected in parallel in a neighborhood. Okay. So here's wiring coming from the electrical system or the FPL or whatever, and all houses are connected in parallel as well. So some of your heavy duty appliances, so what you're getting from the wall is 120 volts, but some heavy duty appliances need higher voltage. So power is voltage times current, and if you want greater power, they provide you with higher voltage. They provide you with two live wires. Okay, so the voltage you're getting out of there is something like this: amplitude sine omega t. Okay, so if you want higher voltage, they will provide you with two live wires, sine omega t minus a, and you're using the difference in voltage between those two, sine omega t plus pi, and you have had trigonometry, and you can use your sine of a plus b formula, and what you get is 2 times sine omega t. So you have twice the amplitude. Instead of 120 volts, you have 240 volts. Okay. So you can use that to run your washing machines and stuff like that. Okay, so there are two live wires out of phase by 180 degrees. Okay. The utility provides two live wires 180 degrees out of phase. So this is the stuff that's in your garage. Okay. Let's say here's a wire going through the back of your wall and it's running your fridge, let's say that's a 10 amp current. What if you have a voltage surge and then the current, for a brief period, the current was 20 amps here, rose up to 20 amps. What will it do? It will fry the wire behind the wall. And now that fixing that thing can be a pain. You don't want to be breaking down your walls every time you have a thunderstorm. So how do you prevent that? So you have these circuit breakers in your garage. Okay. So the current will go through here. This is a bimetallic strip. If the current is too much, if the current is too much, with the current this thing gets heated, and this bimetallic strip is such that if you raise the temperature, this guy expands more than this guy. And so this will bend in that direction, and that falls in this slot. The spring pulls it down, and the electrical connection is immediately cut off. Okay. Preventing that large current there, preventing you to have to break down your walls every time. So that's, the circuit breaker is like a fuse, but it's better than a fuse. Why is it better than a fuse?
It's reusable?
Yeah. Yeah, and the fuse, you got to go find it and replace it. Here, you just flip the switch back. Okay. All right, the next few slides are about how your nerves work. You want to hear it? It says you'll have to be a little patient about it. It's a little involved. Okay.
That was what I was most interested in when I saw you scrolling through anyway.
Okay, all right. So as far as, okay. So one way to look at a person really is, you really are 90 billion interconnected neurons. You're really this most powerful computer. The rest is all accessories. That's one way to look at it. All right. Okay, so you are a really very powerful computer. And so we'll see how your nervous system works. Okay. So you have sensory neurons that are bringing stimuli from the environment. Okay. Then if there's some processing going on, that'll go on here. It's auto response anyway. So, and then you send out a signal to react to that stimuli. Okay. If this goes to the brain, of course, in the brain processing will happen, and then you'll. Okay. The signal here travels at about 100 meters a second. A nerve impulse will travel 100 meters a second. Okay, and that's makes sense. Let's say, why do you want that? I mean, faster the signal, it costs you more money. Okay, so let's say you touch something hot. Here's a meter. If it travels 100 meters a second, that information gets to your brain in 100th of a second, which is 10 milliseconds. Then you process and send back. So all this can take maybe 30 milliseconds. And that's enough to pull back from a hot plate. If the signal travels too slow, if you reacted in 2 seconds, you'll burn your hand. How about reacting in 2 milliseconds? Well, you're certainly not going to burn. Why not react in 2 milliseconds? I'm sorry? It's costing you more energy to react that fast. Okay, well, maybe. So it's a more costly system. Okay.
What about actual reflexes?
I'm sorry?
What your reflexes? Like,
That's the reflex. Your reflex is.
Like when the automatic reflex, like when doctors hit your knee.
Okay, so there, that signal is going through the spine. It's not going through your brain. So that's the auto reflex. So there, 10 milliseconds, 0 milliseconds, 10 milliseconds.
So it's like
Yeah,
that.
that's all. I mean, so, yeah, there are situations where you don't have to think. I mean, so Christina asked, can she take the test next week? I don't have to think. No is the answer. You know? So there are situations where you don't have to think. Okay. So that's the kind of stuff. Okay. All right. So anyway, nerve impulses travel at about 100 meters a second. And we'll see how nerve impulses are. Okay. So here's a neuron. You have 90 billion of these guys. This is an axon. This, by the way, is a myelin sheath. This is an energy-saving device, sort of. Okay. Nerve impulses can jump across these, and when this guy goes bad, there's some disease. What is it called? I forget the disease. Those people are always tired and they're using too much energy. Is it, not Lou Gehrig's disease? Huh? MLS? Anyway, look it up. There's a disease of when the myelin sheath goes bad, okay? So there's the axon. The longest axon in a human body can be about 1 meter long. Yep. These are the dendrites, okay? You talk to other neurons through here, and other neurons are connected to here. So here's how these guys are connected. Okay? An axon from one neuron will come here. And generally, when you learn things, you're making new connections and stuff like that. Okay, so the largest axon in the human have a diameter of 0.2 millimeters. So the diameter of that axon is 0.2 millimeters, the largest one. Yeah. A giant squid has one with a diameter of 0.5 millimeters. So use that to study, good for experiments. Okay, anyway. Okay. Nerve signal travel at about 100 meters a second. Neurons transmit signal as voltage pulses. Okay, so this is a nerve impulse. Here is a voltage pulse. Okay, so what this is showing you is the following. So here is that axon. What is the resting potential in the axon? What is the resting potential inside a cell? It's inside the cell, it's minus 70 millivolts. And okay, so 0 millivolt, 0 volts. Okay, so the difference is, okay. So what this is, okay. So what this is showing you is the following. So here is the 70 millivolts, and at this location on the axon, the voltage has gone to 0 and then back. So this is the nerve impulse, and this is what travels at 100 meters a second. That is a nerve impulse. So in this location, in all these locations, the voltage is normal inside this tube. At this location on the axon, the potential has gone to 0 volts, and then it resets back to negative 70 millivolts. So we'll understand this nerve impulse, how this happens. And this is about 3 millisecond width wide. Yeah. All right, so here's a nerve impulse traveling along the axon. Okay, now you pinch yourself. You pinch yourself harder. There's a difference. So what's happening? I'm sorry? Okay, so the strength of a signal is conveyed by the number of pulses transmitted. So if 10 pulses a second go, it hurts so much. If it hurts more, that's 20 pulses a second going. Okay. If something is hot, mild, you're getting 10 pulses a second. Medium, 30 pulses a second. Thigh hot, that's infinite pulses. All right. So the strength is conveyed by the number of pulses. Okay, so now we'll understand this single pulse. Again, this is something, see, this is milliseconds. See, this is about 3 milliseconds, 4 milliseconds wide. All right, so here's a voltage pulse. Okay, so this is the 70 millivolts inside. Okay, so, and then at this localized location, the pulse has gone to plus 20 millivolts. So inside, the voltage is plus 20 millivolts. And then it goes back and resets to negative 70. All right, so here's how it works. Okay, so here, now this is the axon. Inside the axon, here's a picture inside the axon. Here's the cell wall. This is the cell wall. Okay. And inside the cell, you have potassium ions and large negative ions. Okay, so it's outside, it's essentially seawater, sodium and chlorine ions. Okay. And then you have these channels whose behavior can change. Under normal circumstances, the channel will permit potassium ions to go and doesn't permit any of the other ions. Okay. And since the concentration of potassium ions is higher here, they diffuse just randomly. Okay. And none of the other can go in, so you see potassium ions go out, so you're left with negative ions. And the potential here is negative. So the resting potential, that's how you get a resting potential of negative 70 millivolts. All right, now let's say you touch something hot, or you pinch yourself. Okay. Or even if you touch yourself. Okay. What happens is you change the surface properties. You open up the channels. Okay. You change the channel property. You change the channel property, and now sodium ions can flow in. Remember, this was negatively charged. There was excess positive charge, and you change the properties of these channels, suddenly sodiums will flow in, and that negative potential will go to zero potential. That's how okay, so you change the channel properties, sodiums went in, and suddenly the potential went to zero potential. So at that location, you change the potential to 20 millivolts, plus 20 millivolts. Okay. And then, of course, since this has become zero again, so inside, it's the resting axon potential is and always permeable. Okay, resting axon membrane is slightly permeable to sodium, very permeable to potassium, and always impermeable to the negative ion. This leads to the negatives. Okay. Appropriate stimuli change the membrane properties locally, leading to an inflow of sodium ion lasting about 2 milliseconds. This produces the plus 30 millivolt peak in the action. Immediately afterwards, an increase in potassium inflow out of the cell restores the resting potential. Okay, so what happens is now once the sodium have gone in and the potential has gone to zero, now potassium ions is still higher in concentration, so they'll flow out. They'd stop flowing because of the electric field that was opposing their flow. There were too many, this region was positive. But now that this has become neutral, the concentration of potassium is still high, they'll still flow back. They'll start flowing back again. And that'll go back to 70 millivolts. And the potential has gone back to 0 volt, to 70 millivolts. Okay. And then this impulse will travel. So that's how this nerve pulse is generated. Okay, once the nerve pulse is generated, now what has happened? What is the end result? When a pulse passes here, a whole bunch of sodium ions are outside, and a whole bunch of potassium ions are outside, and a bunch of sodium ions are inside. The pulse has gone by. Now you have to clean up the mess. What do you have to do? You have to bring back these guys, the potassium ions, and you got to shift these sodium ions out. 20% of your energy goes for that, for the ion channel. Okay. All right, so that's how the nerve impulse travel. In an axon, charges move, so the nerve impulse is traveling in this direction and charges are moving back and forth in this direction. Move perpendicular to the nerve signal movement. Okay, so this is unlike in wires.